In this video, we're going to talk about what's known as the combined gas law. So P1 V1 over T1 equals P2 V2 over T2. This is the combined gas law. And that is on table T in your chemistry table for New York chemistry and the New York Regents exams. And so what we have to do again, because it is a gas law, we have to convert all temperatures to Kelvin. Because again, a conversion or a doubling of temperature in Celsius is not the same thing as a doubling of temperature in Kelvin. So you can check out the Gay-Lussac's law, you can check out the Charles law, you can check out the Kelvin to Celsius conversion videos I have, and they all go through examples just to show you how that is. And so what we're looking for are all three things: pressure, volume, and temperature. And sometimes they might not always be given. So notice sometimes in this first question we see STP. So we need to know to look on our reference table. And in your reference table, we have certain STP values. So STP, we have 0 degrees Celsius or 273 K for temperature. That's our T value. And our P value, 101.3 kilopascals or 1 atmosphere. Those are the ones that are given on your reference table. Another one that is frequently used is 760 torr or 760 millimeters of mercury. They all mean the same thing. Just like 12 inches is 1 foot, these all mean the same thing as far as equal amounts. And so when we look at our values, we have 3 values, and then we want to know what the other one goes to. So a sample of neon is collected at 2.7 atmospheres, 12 degrees Celsius. It has a volume of 2.25 liters. So there's my 3 values: pressure, temperature, and volume. But I got to convert my temperature to a Kelvin temperature using the formula again. K equals degrees C plus 273. We've seen that on a couple scenarios, that on a couple previous examples. This is a plus symbol, not a funky looking T. And it's also on the back of the reference table T as well. So 12 degrees Celsius is 285 K, because I'm just going to plug in 12. 12 plus 273 is 285. So when I go and set my value up, again, every time, P1 V1 T1, P2 V2 T2. So my P1, 2.7 atmospheres. My P2, or my V2, excuse me, is going to be 2.25 liters. And my V1, sorry, P1 is 2.7 atmospheres. V1 is 2.25 liters. And my T1, 285 K. What I go to, my P2, V2, and T2, it says, what would the volume be? Okay, that's what I'm trying to solve for. What would the volume be if it's at STP? So at STP, I got to pull from these numbers based on the system that I'm using. Because I'm using atmosphere, I got to use my atmosphere number. So 1 ATM. Because I'm using Kelvin, I got to use my Kelvin number, 273 K. So now I have V2 by itself. Now it's just a mathematical expression. And a lot of times, again, the state on the Regents exam will have a question. We'll have a question, and we'll just say, show the correct numerical setup. If you have this, you'll be done, you'll be golden, and you'll get the question correct. Or if you do some version of this, because you could also cross multiply the 273 and the 1 by bringing it up and down over here. For example, multiplied by 273K and 1 ATM, because that's going to get rid of it, because I want to get V2 by itself, but I also have to do it on this side. So if I multiply by 273 and divide by 1 ATM to cancel those out, so I'm canceling out 1 ATM, I'm also canceling out 273, I got to do that over here. 273K and 1 ATM, and what we're also going to get rid of, I'm going to get rid of my ATM unit, I'm going to get rid of my K unit, and that's going to be left with liters, which is good because I want to solve for volume. So if you had this as an answer, if you just wrote V2 and you had all of this stuff as your answer, 273, 27, 25, 1, and 285, that would be a correct way to show it as well. Okay? Now, what we need to do in our calculator, this one is a little easier because there's a 1 here, and we don't really need to add and do anything to that value because it's not going to change the math. But basically, anytime you have calculations with multiple values in the top and the bottom of your denominator, or top of your numerator and the bottom of your denominator, everything in the top gets multiplied, everything in the bottom gets divided. So 273 times 2.7 times 2.25 divided by 285. I could say divided by 1 too, but it doesn't make sense to actually do that because it's not going to change the number. But if this was a number 2, let's say this was 2 right here, it would be 273 times 2.7 times 2.5 divided by 2 divided by 285. Again, that was if this was a 2. It's not, but if it was a 2. So anything on the top you times. Anything on the bottom you divide. Because on the actual exam, you're only going to be able to use a cheap generic 4-function calculator, and you're not going to be able to do different functions. You're not going to be able to put parentheses like you would with your scientific and your graphing calculators or with a computer. So you need to keep it basically simple when you do it so that you also don't do multiple steps. So again, 273 times 2.7 times 2.25 divided by 285. And at the very end for this question, V equals 5.8 liters. Okay, that's what we would end up with 5.8 liters. All right, let's do another example. A sample of argon has a volume of 205 centimeters cubed when its temperature is minus 44 degrees Celsius and its pressure is 712 millimeters of mercury. What would the volume be of argon at STP? So again, we're going to be using STP values, but we have to do a couple conversions. So minus 44, if we plug minus 44 into this equation, basically 273 minus 44, we get 229 K. So we need to know that for our example. So first pressure, 712 millimeters of mercury. First volume, 205 centimeters cubed. And my first temperature, 229 K. And what that equals, if we know it's going to STP, again, 760, because we're using millimeters of mercury, 760 millimeters of mercury. I want to know what would the volume be again, times V2, and my temperature, 273 K. So when we take a look at this, this is very similar to this other question where I could flip the numbers and go back and forth. But notice now I have a different number than 1. Before up here I had a 1 over here, so this is where it's going to make a little more of a difference. So I have to get rid of this. I got to multiply by 273K. I got to divide by 760 millimeters of Hg. That's going to get rid of it on, there's my Kelvin gone, here's my millimeters of mercury gone, and then I'm left with V2. But if I do it on this side, I got to do it on this side. So 273K on the top, 760 millimeters of Hg on the bottom. Notice I'm going to have millimeters of Hg I can cancel, millimeters of Hg. Now I don't cancel out any numbers, just the units. Cancel out my K, cancel out my K. I'm going to be left with centimeters cubed, which is a volume unit, and of course what we want to solve for. So again, this is where the calculation comes into play. Anything on top we multiply, anything we have on the bottom we divide. So 273 times 712 times 205 divided by 760 divided by 229. Again, times, divided by. If you want to do your own calculation, you could do all three of these or 273 times 712 times 205. You can multiply those and get a number. And then I could multiply 760 and 229 and get a new number, and I could take those two numbers and divide them and still come up with the same answer, but it's just more steps. I like to do it with all one look and then just enter in the calculator. 273 times 712 times 205 divided by 760 divided by 229. And we're done. V2, in this case, as we go through and we do all the math, V2 equals 229. Okay? It just happens to be the math that ends up being 229 centimeters cubed, which is interesting because the volume, or the original temperature, was that same number. And so it just happened to be that the calculations worked out that way. Okay, it doesn't always work out that way, it just happened to be that way. Now, I want to do one that has a different flipped value. I just got to find the right question. And we're going to go over to this page, we're going to go over to the other page here. I'm going to flip here to one of the other examples, make sure I'm on the right question with the right value. Just confirming with my answer key. Again, that's why I'm doing these numbers so quick. I'm not pulling the math out of my out of the air. Again, I have it written down on a separate sheet. So I have 2.9 liters of gas and a pressure of 5 atmospheres with a temperature of 50 degrees Celsius. What will the temperature of the gas what will be the temperature of the gas if I decrease the volume of the gas to 2.4 liters and decrease the pressure. So I'm actually telling you the differences in what's being changed in this case, unlike the previous questions that said STP. And so what we need to look at, we have 1, 2, 3, 4, 5 numbers. Okay, we have 5 numbers. We're always going to solve for one. The question says, what will the temperature be? We want to know what will the temperature, the new temperature. And so we do have to convert to Celsius. So 50 plus 273 is 323 K. So if we set up our first pressure and our first volume and our first temperature, those three, first pressure is 5 atmospheres, first volume is 2.9 liters, first temperature is 323 K. I decrease the volume. I want to know what the new temperature is, T2. The new volume is 2.4, and the new pressure is 3 liters. So very similar, we have a cross multiplying and dividing, but now my value is down here at the bottom, okay? So if I multiply, again, you may find easier ways to do this. If the state asks to show the numerical setup, we would be done. We've shown the numerical setup. But if you need to solve for the actual number, again, I got to do cross multiplying and dividing. Basically, I have to, everything over here I have to flip. And so I would do the same thing over here. I would bring this up T2, but then I got to bring everything over here. So if I multiply, this side, I got to multiply that side by T2. So we're going to multiply this side by T2 and multiply this side by T2. And so I get rid of T2 on that side as far as a denominator goes. So now it's actually in the numerator position. But now I got to get rid of all this stuff by basically just doing the opposite. So I'm not going to do it on both sides. Hopefully you understand about this by this point, because I would multiply by 323 on the top over here. So I'm going to multiply 323K on the top over here. But I'm also going to bring these two down and divide by. So I got to do the same thing over here. So 5 ATM and 2.9 liters. And so checking my units, I should have ATM there, not liters, because my ATMs are going to cancel, my liters are going to cancel, and I'm going to be left with a temperature up on the top. And so this will have all canceled out because we basically got rid of it. So we have 3 times 2.4 times 323 divided by 5 divided by 2.9. Again, 3 times 2.4 times 323 divided by 5 divided by 2.9. Sorry, we're off the sheet there. Okay, so anything on top gets multiplied, anything on the bottom gets divided. So my T2 in this case is going to end up 160K after those changes. Hopefully you found some benefit in these combined gas law equations. Feel free to reach out, ask a question if you're still uncertain, or if you're one of my students, stay after for some extra help. We look forward to seeing your successes. Take some action. Make sure you always set up your equation first and then substitute. Make sure you're converting everything into Kelvin, because again, a doubling in Celsius is not the same thing as a doubling in Kelvin. Again, this has been Mr. Gardner with chemistry, and we look forward to seeing your success.